Great. Well, good afternoon. I really have the pleasure of following up on this very nice setting of the stage for Andrea, and we're now going to be shifting from the things that we know how to do into the things that we're still learning how to do. How do we process this information about changing earthquake activity to provide robust estimates of the change in the earthquake hazard? So the figure that we're looking at here is the new National Seismic Hazard Map. It's one realization of the model. This was released in July of this year, and it's designed to provide an estimate of earthquake shaking that is primarily designed toward the building codes. In other words, low probability events that may occur for which we want to make sure the buildings are designed adequately. And to look a little bit more about why we make these maps, these are, first of all, probabilistic estimates of what may happen in the future, and they're typically very low exceedance probabilities for U.S. maps, typically 2% in 50 years. That translates to an average return time for a random process of once every 2,500 years. Now, ironically, that's the same rate at which a tornado could be expected to pass through your house in Oklahoma. Low probability events, but both of them potentially with high consequences. And again, these are the maps that typically underlie all of the seismic design provisions in U.S. building codes. They do assume a time-independent rate of earthquake occurrence, and of course that's one of the challenges when we've seen that earthquake rates are changing by orders of magnitude. We typically develop these from geology, geodesy, and seismology in the western United States. For example, in California, we can use all the information that we gain from GPS and other ways of studying the deformation, the way that we can map and understand the faults, the rates of movements, seismicity, to develop models that allow us to make a physics-based prediction of ground motion. But in most of the rest of the United States, we depend upon the seismicity as a way of understanding what the rates of earthquakes will be in the future. And typically these are areas where seismicity occurs at low rates, so we're measuring a small signal, and we're trying to make the assumption now that this signal is from a constant rate Poisson process. And in the development of this map, it was very intentionally decided that these little black polygons you can see here, the areas that, many of the areas that Andrea discussed, the increased seismicity in these areas were ignored in making these maps. And basically the reason that the team in Golden did this was they were not sure how we should project that information forward when you're looking at a return period of 2,500 years. I don't think any of us think that these new rates of activity are going to continue indefinitely. So the question is what to do about this. Well, and again, I mentioned that this map was released in July. I want to step through very briefly just the elements that go in to make the map for those of you who are not familiar with them. There are really kind of three basic steps that are followed. The first one is to make an estimate about where earthquakes will occur in the future. And we may do this by looking at faults. We may look at an aerial source, which earthquakes are occurring. We may consider a distribution of earthquake sources. So we set the stage for where earthquakes will happen in the future that will generate the ground motions that go into the map. We then need to decide how often earthquakes will occur, and very, very often what we're using is a Gutenberg-Richter relation or some other way of projecting small earthquake activity into the future. And of course this will depend upon both the activity level as well as assumptions made about the largest earthquakes that may occur, because that's where the hazard largely lies. We then need to combine these things with ways of estimating the ground motions that will occur in these earthquakes. How hard will they shake the ground? These all get folded together with these elements, and then we can take all of this information and put it together to develop a hazard model going forward. So the challenge for us has been that in developing the map, it was decided to basically project this straight line forward for the purpose of establishing a base, and then we're going to work from that to try to incorporate the changes that have occurred. You've seen this curve before, and Ernie also showed you this one, indicating that in Oklahoma in particular, the rate of earthquakes is about twice as high as it is in California. So these are the challenges, and we have to figure out how these earthquakes are affecting hazard. We need to know how much higher it is, make that a quantitative number. We need to understand where it's increasing, and we also need to be listening to the users to find out what types of information they need. Maybe they don't need a 1 in 2,500 year map. Maybe there are other tools, other information that they will find more useful in terms of the decisions that they're going to be making. So to get at that, we held a workshop in Midwest City last November, which was co-hosted by the Oklahoma Geological Survey. We were fortunate to have about 150 people participate in the workshop that included many people from industry. There were state and federal geological surveys represented, people from academia, importantly regulators from many of the different states where they have increased seismicity, people from the insurance industry, transportation agencies, and so on. So these are the groups that use this information, and we wanted to meet with them to both convey to them our understanding of the current situation, but also to listen to them to find out what type of information they were most interested in receiving. And I think it was somewhat a surprise to the hazard modeling community that people are mostly interested in knowing what's going to happen next year. So our current focus is going to be on translating the information of the kind that Andrea was describing into a model for what the hazard may be in the coming year. This is a model which I think can be updated pretty much continuously once we have it in operation. But the current goal is now to develop models that go forward in time. And what I would like to do now is to step through some of the issues that we're still thinking about in terms of how we go about developing these models. So in step one, we said we need to identify the areas where the earthquake rate is changing. And I think Andrea has probably convinced you that we have good tools for describing where the earthquakes are no longer being adequately modeled by the Poisson assumptions that were being made in the past. So in terms of identifying areas with rate changes, that's something that I think we have fairly well in hand. And we can do that both in space and time. She also indicated that there is some hope for developing new tools that use other types of information. For example, if we could learn how to develop a quantitative way of using, say, drilling information, injection information, there are many types of data that potentially could allow us to develop a more predictive model of where seismicity will be occurring. The problem with using this year's earthquakes to predict next year's earthquakes is we'll do a good job where this year's earthquakes will occur, but they will not inform us about new areas that may be occurring, showing seismicity. And this is where we hope that some of the type of industrial information that is available in most states will be helpful. So to look at how we might go about accounting for changes in the earthquake rate, she also showed you that by using change point methods, we can really pretty accurately determine both where and when small changes in earthquake rate are occurring. And these can now be folded into the models, particularly if we are using a Poisson assumption over a short period of time. In other words, to assume an earthquake rate based upon what is happening today. It's going to be a little bit trickier to understand what to do with the magnitude-frequency relationship. Here I'm showing some cumulative magnitude-frequency curves for Oklahoma. This is Oklahoma Geological Survey data. All of the curves clumped together here cover 1970 through 2008. You can see it's a very constant process. 2009 through 2013, we're up by about an order of magnitude. 2014, up by another order of magnitude. Well, it's very clear that the A value, the height of these curves, is going to have a very big impact on hazard. What's not as obvious is that as long as we assume that larger earthquakes can occur, it turns out that the maximum magnitude is not a terribly important parameter. Scientifically it's of great interest, but it is not one of the things that drives the hazard. One thing that does drive hazard, however, is the B value. And I'll look at that in a little more quantitative detail here at the end of the talk. So think about A and B as maybe the most important things that we're going to be gaining out of these magnitude frequency distributions. So another way we can think about the rates is how we combine what we've done in the past with what we do going forward. We have a branch zero in our logic model, logic tree, which would say that we're going to ignore the rate change. So that was what was done in developing the 2014 map. Some alternatives would be to say, well, let's just average everything together and take that new rate. The problem with this is that it's very difficult to describe statistically what that model should be because it's clearly not a Poisson process. Another way would be to take the sharp rate increase as the current rate and project that forward. That probably is what we'll be doing in terms of developing a one-year map, but it's clear that that is not an appropriate thing to do if you're developing a 2% and 50-year map. We also want to think about the possibility that these new earthquakes could come from a distinct population, in which case there may be a very different max. For example, I think that most of us feel that hydraulic fracturing, while it produces many small earthquakes, has a very small probability of producing earthquakes large enough to be felt. That is our experience, even though there have been earthquakes of about magnitude 4 now associated with frac jobs. They're probably very unlikely in producing magnitude 6 or 7 earthquakes, and we should account for that if we can identify which earthquakes are occurring during frac jobs versus other types of activities. And finally, we should think about the fact that these changes are going to be transient. So maybe over a one-year time, we don't need to worry about that. But if we're interested in making a 5-year or 50-year map, that is going to be an important fact. And of course, if we look at the Denver area, the Rocky Mountain earthquakes have pretty much faded away. But understanding how these processes fade away once the industrial activity ceases is one of these unsolved problems. And then in step 3, we have the question about what ground motion equations are appropriate. There's a lot of work going on about this. I think one thing that we can say is that looking at the observations at near distance from many of these earthquakes, we see that many of these earthquakes are occurring at shallow depth, and that typically in the shallow basement, and consequently, any ground motion model that we use needs to include focal depth as one of its parameters. The old models didn't consider depth. The new models need to have depth if they're going to be applicable to these types of earthquakes. I think the other thing that we can say is that the ground motions actually are very comparable to the earthquakes that we know a lot about, those in the western United States. Gail Atkinson has a paper that's submitted that discusses this, and here are some examples of some of the recent earthquakes. This is a magnitude 4 earthquake in Timpson, Texas, 0.6 G's horizontal acceleration, 22 centimeters per second. Did some damage to the usual kind of suspects. Here's some damage from the recent earthquake in Kansas. Again, relatively high levels of ground motion close to the source. So these are nuisance earthquakes in some sense, that they don't have, the magnitude 4s probably don't have potential to do serious structural damage, but they are going to produce ground motions that people will be concerned about. So to get at these questions, we have put together a draft logic tree. And this is where we try to expand what we know to cover the epistemic uncertainty in our knowledge and provide independent ways of working through the decisions that must be made to develop a hazard model. The model is currently divided into these elements, a catalog of which there are choices between clustered and undeclustered catalogs and rate models that are based upon different cutoffs and b-value assumptions. We have a rate model which is also divided into looking at catalogs of different time periods. We are concerned about how to smooth the earthquakes. There can be very broad smoothing, as is typically used in the maps, or we maybe use very smooth, very short distance smoothing, just 5 kilometers. We also have to consider what the maximum magnitudes may be, and we have a whole suite of ground motion models. So I'm going to show you an example of this work in progress. These are not final maps by any stretch of the imagination, but we're going to look at what happens as we go through these logic trees by first taking the undeclustered catalog. And I think Andrea should have convinced you that this is important to do, because these sequences typically produce many earthquakes. And collapsing all of those earthquakes to one does not really reflect the ground motions that will occur. We're also going to use the 2014 catalog to get the most updated rate. We're going to use very narrow smoothing, just 5 kilometers, so we assume that the earthquakes are not going to migrate very far. And we're going to use the standard assumptions about Mmax, and we're going to consider all of these ground motion models, just weighted equally. So I'm going to show you a couple of maps of ways of displaying this information. These are maps that Chuck Mueller just made this past week, so they are really hot off the press. So this map, again, assuming the 2014 base for the background, earthquake rates from earthquake rate increase in 2014, the undeclustered catalog, the short smoothing kernel, and all of these ground motion models. So on a 1% of exceedance in 1 year, this is the map we see, and you can see that it's this north central Oklahoma area, which is the bullseye. The ground motions are not trivial. This is a 5 hertz spectral acceleration, and they're typically around 1 G or a couple of Gs in these areas. So this could be significant ground motion. If we look at the 0.04 probability of exceedance in 1 year, so this is the 1 in 2,500 year map, if you will, but now just discussed in probabilities of 1 year, you see that the picture does change. So, of course, Oklahoma is still hot, but now we begin to see the tectonic activity in New Madrid and in Charleston. So it gives one a flavor as to what these maps are going to be. We don't decide how they're going to be used, but we want to make maps that are going to be useful for those who have to make decisions, such as which bridges need repair. As the last example, let me show you a couple of hazard curves. This is the hazard curves of Fort Worth, Texas, and for Oklahoma City. The base case from the 2014 map is shown in black, and then the elevated curves represent current conditions under different assumptions. The blue curve here represents the declustered catalog, so this deflates the answer somewhat. And the difference between the red and the blue here is the assumption about the b-value. The dotted line here is for a b of 1, the solid line for a b of 1.5. And you can see that's one of the main drivers. So that's clearly something we want to understand. But in every one of these cases, regardless what the probability or what the spectral acceleration is at 5 hertz, you can see that we're substantially elevated above the background. So in summary, probabilistic seismic hazard analysis, we think, provides the appropriate framework for developing short-term forecasts of this increased hazard. The hazard is currently, our estimate of the hazard is currently very sensitive to the epistemic uncertainty in our models. We need to work on all of these, but targeted research, I think, is really moving forward in terms of reducing the uncertainties here. And I think to the future, the thing that we need to be looking for is developing better physical models of the process, how we can use other information that will be more informative about making accurate predictions about where changes may occur that have not yet been seen. With that, I'll thank you and take any questions.
Questions for Bill? Yes.
With this big increase in seismicity in Oklahoma, is it sort of decided or determined that all those earthquakes are induced?
So Aile's asking the question about what is the status of our understanding of the earthquakes in Oklahoma, are they induced or not? We don't have an answer to that, but for the purpose of this map, we can actually be agnostic. We don't really need to know why they're occurring, simply that they are occurring. Now, to make a more accurate forecast going forward, I think we will need that type of information. But I think that individual studies are really pointing to the fact that these are being wastewater induced. As I mentioned, there's the whole issue about whether there are other sources, and that's what the next speaker is going to be addressing, I think.